All right, line V1, learning task 11. This is our final video here on the braking methods that we have over here. We're going to go and talk about regenerative braking, and we are going to go and talk about our eddy current braking. Both of these are once again going to be forms of braking that are going to go and dissipate energy as values of heat that we are going to go and see. Regenerative braking is going to go and take from my motor, it's going to go and feed that back into the circuit, and then from the circuit, it is then going to go and feed that back out of the circuits, to external loads, which is where it's going to go and dissipate everything as heat. Sorry guys, Eli's going nuts in the garage over here right now. I don't know if that thing where Cash is going nuts for a bit right now. So the pen's kind of all over the place because he keeps trying to jump on top of that. Okay. Regenerative braking is where we're going to go and act like a generator, and then we're going to go and feed our power back out into the system itself. And we can use it to go and slow down a motor, but it's never going to work to go and absolutely stop a motor because there always has to be current flow, and if we're not generating value of voltage, we would not be able to generate current flow, and therefore we would not be able to actually go and physically stop any sort of a motor. So we do have to go and provide, some sort of a load, and we're only going to be able to get a limited amount that we will get back out of it. The other main issue that we have is that we're not talking about an absolute value of zero speed. We're talking about a value of speed above synchronous speed that we are going to be having this regenerative braking itself actually happening at. Regeneration doesn't happen until we have got our synchronous field. Let's go and just draw a motor out over here. We've got that synchronous field that is rotating. We'll give this a value of 1800 RPM, let's say. And then we've got a load on it. Let's say something that can build inertia momentum. Cranes are a great place. You think about a crane load being released, where we could go and deliver a load that is going to be operating at higher than that. Let's say 1900 RPM, where it's overspeeding. What happens is when I end up overspeeding the rotor, moving the rotor faster than what my synchronous field is on the outside, I'm going to automatically go and get this regeneration that's going to happen. We are going to go and create currents inside of our rotor bars that are going to be opposite to what they normally are, and therefore, as a result, they are going to go and give us retardation or slowing action that is going to prevent us from going into runaway off of these. It is an inherent characteristic of a motor, which means that we don't have to worry about how we would go and make this happen. It just happens automatically. And there's going to be absolutely nothing that is going to be a contact or a wearing surface, so I don't have to do any sort of maintenance. The big disadvantage is it only works in these situations where we are going faster than our synchronous speed, and that's pretty rare in our industry that we're going to be moving everything faster than synchronous speed. So for what we're looking at, it's not really going to be a common method for us to go and slow motors. Last one that we are going to take a look at here is going to be this eddy current braking. And eddy current braking is this cool method where we can go and have fixed electromagnets and then a rotating drum. I'm going to go and call this thing fixed over here. Basically, what it looks like is something like this, where if this is my motor itself, let's draw that out as our motor. What we're going to have is we're going to have our shaft of our motor, and then coming off the other side of the shaft. So this is going to my load. I'm going to go and have an extended shaft. You can get a shaft that goes all the way through the motor. It's not the most common type of motor out there, but it is still relatively common. I'm going to pass that through, and then on the other side of here, I'm going to go and have this drum that is going to go and be placed off of it. Now, this drum doesn't require any sort of a friction. It doesn't require anything that's going to directly be up against. All I need to do is have this drum. It's like a big cup. The shaft is on the other side. The drum itself is going to go and rotate with the motor, and it's going to go around a fixed electromagnet. Now, if I don't turn on the electricity to the electromagnet, there's no magnetism. Nothing is going to go and happen. Therefore, we're not going to go and get any sort of braking action out of it. If, however, I do want to go and stop this motor, so I can go and use the same types of braking methods as what I've seen in anything else, only instead of applying dynamic braking, I would just apply this, or instead of applying friction braking, just apply this. Whatever it would be, I'm going to go and send current through here. And when I send current through here, it's going to go and create eddy currents. And eddy currents are simply just going to be circulating currents inside of this piece that we're going to have. It has to be a metallic piece that's going to be thick enough that it can dissipate any sort of a heat. We're just going to go do a quick set of left hand, right hands to go and establish how this thing is going to be working. First thing I'm going to do is I'm going to go and establish my lines of flux. My lines of flux are going to be leaving the North Pole, traveling out, and then they are going to go and travel. There is going to be around this something else that is going to capture those flux lines. So we will have like another overlapping steel shell. It's going to direct those back in, and then it's going to go and fire them back in over here. We would have the same thing over here, over here, over here, etc. We're just going to examine this one here for now. If we take a look at the conductive drum, the motor is spinning the drum around this in that sort of a direction. Well, if I've got my drum spinning around here in that direction, that means that I have got my drum, which is a conductor, moving past a magnetic field in that same direction over there. If you remember your left-hand rule is going to go and show thrust on the conductor, and it is going to go and show the direction of field that we are going to go and have, and then when you fold out your center finger, you see a direction of current. I want you to do that right over here. If you stick your first finger in the direction of the field, so pointing in towards the south, your thumb in the direction of thrust, pointing up like that, you should see that you would be establishing a current that would be driving in to the drum. If I was looking at the edge of the drum, it's driving into the drum, and it corresponds to the lines over there. Same with up top over here. If I were to go and stick my first finger directly up, my thumb over to the left, because we're rotating in that direction, I would see that on this one, I would have current, if I was looking at the edge of the drum, coming out towards me, and that corresponds with the arrows that they have over there as well. Once we have got those established, what we can do is we can go and figure out our lines of flux around these. So these are just induced currents that are going to be inside here. What's my direction of induced current around here? We'll just use a left-hand rule. And if you use your left-hand rule, you should go and have a current that is going to be circulating, or sorry, a field that's going to be circulating around that one like that, and around this one over here like that. And now that you have got those, what you can do is you can fire out that line of flux again. This time you see that that line of flux as it fires out to the north is going to get caught over here. It's going to get ripped around. It doesn't like that. It's going to come back here where it's trying to go in, and then it's going to get caught, ripped around, and sent back in like that. And we see that this blue magnetic line of flux is going to be exerting. It's a rubber band. It's going to be trying to slingshot these conductors back out in that direction. It's going to go and give us a opposition that we are going to go and have. This is going to go and be where we're going to get the braking. So the braking is continuously going to be happening through here, through these currents that are circulating through this metal. This metal over here does not have to be magnetic. We're not trying to induce magnetism. We're trying to induce current flow. So it can be copper, it can be aluminum, it can be anything like that, that we are going to go and have current that is going to be changing around its direction. But ultimately, we're just grabbing those lines of flux for the current, and we are trying to go and throw this thing back out in the same direction. We can vary the amount of braking that we are going to have as well by varying the amount of DC that we feed into these electromagnets, right? These electromagnets are fixed. Therefore, we just go and stick in a rheostat, and as soon as we stick in a rheostat, then we can adjust the amount of current that's going through here. The more current, the more braking that we are going to get off of this. This one does have some distinct advantages and disadvantages. Advantage is that, once again, we cannot reverse the motor if we apply it for too long. If the motor comes to stop and we still have the eddy current brake applied, we're just going to go and have a magnetic field over here. It's not going to do much, just waste a bit of energy. We can adjust our torque by adjusting the amount of current that we feed through this field rheostat that we have over here. And we don't have any frictional parts. We don't have anything that needs to go and ride along. It's going to be a completely brushless type of situation that we have over here. So we don't need to go and maintain anything that's wearing down or, breaking, etc. As far as disadvantages, it does have a couple. Number one is it's not widely used, and therefore it's going to be a bit more expensive. What we saw over here, where we had to have that drum off of this thing, we saw that we had to have the drum. Inside of that drum, then we had to go and insert this magnet, the electromagnetic core over here, and then we need to still have another drum that goes around the outside of that is then going to go and sit around here, because those lines of flux need to enter and they need to go around and then shoot back across if we're going to have effective eddy current braking. So it does require, where my magnets are mounted on, my magnets are going to be mounted on the inside of another drum that overlaps over top of that other drum that we have over here. It is going to be more expensive than any of my other ones. It's also not going to be available if I lose my value of voltage. If I don't have voltage anymore, it's going to be impossible for us to go and get any sort of braking action off of it. It's just going to be a drum spinning in midair. And once again, when the motor actually comes to a stop, it does not hold the motor. The motor will still be able to rotate. And last of all, because the amount of, e.g., that we are going to have, generated voltage, is going to be equal to my K, phi, and N, or BLV. The amount of volts that I will generate will be directly related to the speed that this drum is rotating around here. The volts will go down as the speed goes down, therefore my current will go down, and therefore my braking action will also go and decrease. Okay, that covers off all of our AC braking.